Hi, this is the first lecture in the vision module of the F110th course. My name is Zirui, and I'll be talking about classical methods in computer vision today. So the vision module has 2 lectures and 1 lab assignment. The first lecture will be about classical methods. The second lecture is about deep learning methods in computer vision. So in today's lecture, we'll first talk about vision hardware and how to get access to cameras on Linux systems. Then we'll talk about camera model and distance estimation, some useful OpenCV functions. And then we'll put everything together and talk about visual SLAM. First is vision hardware. Cameras, we can have different kinds of cameras. RGB camera, event-based camera, or depth camera. And in depth camera, we can have different depth technologies, stereo depth, structural light depth, or active stereo that's combining the above two. So here is showing a diagram of an active stereo camera. Or we can have lidars. So on the F110 car, we only have a planar lidar that's just one line, but in the real autonomous driving systems, we can have dense 3D lidars. So for example, here, this is a point cloud from one scan, just one rotation of a dense 3D lidar scan. So the contrast you're seeing here is the intensity. That's the intensity of the light that's reflected by the surface of the object and received by the sensor. And we can basically do object detection on this image. And of course, as you can see here, sometimes there is some artifacts with this dense 3D lidars, but it is all the pixels with real distance information. And for LiDAR, as technology develops, we used to have only the mechanical LiDAR, which have the rotating parts that's always spinning. Now we're seeing solid state LiDARs. That's only by changing the phase difference between the light that they can project different light for different angles. So if we have a mechanical LiDAR, would always have moving parts, and the scanning speed is limited by these moving parts, so as the beam density. Basically, in a dense mechanical LiDAR, you have to have one emitting and receiving parts for each line you have. For example, if you have a 122 line LiDAR, you basically have 122 receiving and emitting components for each line. However, in solid state LiDARs, they usually just do moving angle scan. So there are no moving parts in solid state LiDAR. The hardware we're going to use is the Intel Realsense D435i. This I means there is a IMU inside. So it is a active depth. So it has a stereo and a structural light projector. This is the structural light projector. This is RGB. So it can produce image depth map and point cloud, as you can see from here. This is the point cloud. It supports most libraries, including OpenCV and ROS2, which we'll be using. This is how it connects. It has a USB port on the side. So each team will get one of these, and this will be used in our vision lab. Let's read its specs and see why do they tell us about these specs. So here is the table of the Intel Realsense. It's 3 models. This is the newer model. This is the model we'll be using. This is the earlier model. The first one we'll be looking at is shutter type. You see here, these 2 early versions are rolling shutter. This newer version is a global shutter. What are the difference? Here we can see the difference. Rolling shutter is you are capturing the information from this CMOS or CCD line by line. And when you're scanning line by line, there's always a difference between the first line and the last line. So when the object is moving really fast, you get this jelly effect, for example, over here. However, global shutter is every pixel has a counter behind it. So when they do the image capture, every pixel is counted at once. So you'll have this jelly effect. So if you have rolling shutter, it's usually cheaper. With high resolution global shutter, sensors are far more expensive than just rolling shutter. But global shutters are better for high speed objects. Next item we'll be looking at is this pixel size. People always talk about like pixel numbers. How many pixels do you have? But in fact, the pixel size is more important than the total number of pixels you have. And the general rule is the bigger the better. With better pixel size, you have more light gathering. More light gathering is more information. So less noise, better noise, signal to noise ratio. And basically, if you compare it to the same lens, your image will have more detail if your pixel is better. For example, this is the Apple's marketing. You have a much larger sensor, but it's true. The sensor it's actually the most important progress you can have. And if we go back to here, we can see the newer version. It's more than double the size of the previous one. So it will definitely have a better performance in low light conditions. Next, we'll look at this field of view. So the field of view means how much angle of the environment this camera can capture. And it's related to the sensor size of the focal length. The longer the focal length is, you have a smaller field of view. And the bigger the sensor size is, you usually would have a bigger field of view, but that also depends on how, what is your lens. If your lens doesn't support a bigger sensor, then you are clipped by the lens itself. But they're related in this relation. It's quite useful when we talk about cameras. Then the next spec we'll be looking at is connector. Why is connector that important? So the Realsense camera use USB Type-C. Why don't they use Type USB 2? Usually for webcam it's USB 2, right? And the answer is it just needs more information. It needs more channels. There are 3 camera connectors that are on the Jetson. These are actually pretty common ones when you're talking about embedded camera systems. The first one, we can do Ethernet. There are many cameras that actually just do Ethernet. Each camera has an IP address, and with Ethernet, you can just connect to a lot of cameras, right, with a switcher. However, Ethernets are quite slow, and the total bus over here is only 1 Gbps. Or we can use USB. It's easy to use. It's also very expandable. But you share a bandwidth of 5 Gbps if you are using USB 3.1. And with USB, there's no direct connection to the ISP. This is a quite important part of the SoC. Then you can see, look at here, this is called a CSI connector. It's 10 Gbps per 4 lane. So usually one of them is 4 lanes. It's dedicated bandwidth. So you don't, for each camera, it's not interfering with another camera or other components that are being connected to the CPU. and it usually has direct connection to the image signal processor. So what is an image signal processor? It's a specialized chip for image processing. It's becoming a more and more important part of the SoC. The ISP can handle image denoise, resize, transform, filter, auto exposure, auto byte balancing, or even something more, much more faster than CPU or GPU. So it's like a specialized chip only for processing images. If we look at here, this is the brand new Snapdragon 8 Gen 1. It has 3 ISPs. Why do they use 3 ISPs? The answer is because most phones have 3 cameras now, and to do some like denoise, they want to capture the image from 3 cameras altogether so that it can be processed with these 3 ISP. This 18-bit just means it's a high dynamic range. So for our Realsense, the Realsense actually has a onboard SoC. So it has a ISP on board to deal with auto exposure or auto white balancing, that kind of stuff. Okay, next is how do we access the camera images on Linux systems? So in Linux, every device is mounted as a file. Cameras are the same. If you connect the camera to the Linux system, it doesn't matter which connector you use. It's always, if the driver is recognized, then it will be mounted as a file. So after you connect your camera, you can use LS to see whether your system has recognized your camera or not. For example, if we connect our Realsense to the Jetson NX, it will be automatically recognized. It will show as 3 files, 3 directories. The first one is the 16-bit depth. The second one is the infrared. The third one is the RGB. So for the lab, we'll be only using the RGB. If you want to use the other 2 for, like, for example, final projects, you can install the official Realsense SDK. They actually have like ROS2 support. It's quite useful. It's quite easy to use. So this image for Linux V4L2, if you're going to work in the vision and embedded vision part, you will be very familiar with this. It's an API to access camera on Linux. So this V4L2 can be used to capture video from any supported device, and most devices supported V4L2. Or it will support, some of the devices will support OpenCV. But for example, Realsense partially support OpenCV. So some of the command, for example, if you want to change saturation or brightness, it may not be supported by the OpenCV, but it will be you'll be able to change it using the V4L2. So what showing here is just a pipeline using OpenCV of how to get images from camera. You can see over here we passed a pipeline. Well, why is it called pipeline? It's, if you look at this mark, it means a pipe. Like you take this information, you pass it to this, and then you pass it to this video convert, and then you pass to this, and then you pass to the sync. Usually there's some kind of sync over here. Then the image can be captured by OpenCV, then you can process it or display it with CV2. Here's another command, V4L2 control, that lets you control the whatever menu the camera has. So if you can tap this after you connect it, it will show a menu of different options that you can have for example, the Realsense RGB camera. Yes, that's the command. Then you can also list what type of format this camera supports. Here are a list of them. So the camera only supports these. It cannot just do in between pixel like formats. And you can see the speed over here. For example, if we want the camera to work in 60 Hertz, then this is the only resolution we can use over here. Okay, since we have the camera connected, we can access the image. How can we relate the objects we see on the image with the object in the real world? We need the camera model. So the goal for this camera model is to get a transformation between three coordinate systems. First is the 2D image pixel coordinates, just the row and columns on the image. The second coordinate system is the camera frame. The third one is, of course, the world frame. And here's what we're going to get. I'm just going to put it here. So we are going to get a transformation that's between this pixel and the camera frame, and will be just one matrix plus a scale factor over here. So we can only get this information up to a scale factor. Of course, that's because things are larger or things are closer. They are actually equivalent. So it's just a matter of scale. So this matrix is called the camera intrinsics. That's between the image and the camera frame. So between the camera frame and the world frame, there is another term called camera extrinsics. We'll talk about these things separately. First, what is the intrinsics? This is a diagram of the pinhole camera. So this image plane should be here. Like there's an object over here. Its light is coming through the pinhole, right? And it's falling on the image plane. So image plane should be here, but it's getting dragged over here just for the ease of showing this diagram. But it's the same thing. It's just like similar triangles. So this will be the capitalized XYZ is the camera coordinate system, camera frame. The small ones are the image pixel coordinate. An object over here, big X, is being projected on the image screen over here, right? And if we turn it into a 2D diagram, we can write down this relation. This X, X is the X coordinates on the image, is related to the X coordinate of the camera frame in this relation, right? The F is the focal length. And if we write it into the matrix form, just directly write this into the matrix form, we get this. There are two terms. That's just because this image center, it just may not align with the center of the camera. That's a mechanical problem. Sometimes the manufacturing of the camera is not very good. It's just misaligned, so you get this effect. So over here you can see there's a lambda is the scale factor. This is called the intrinsic matrix. It has focal length in the X direction, focal length in the Y direction. The center of the image of the X axis or the Y axis, and these are the coordinates in the camera frame. Then yes. Yeah, one thing to note that it's the focal length unit is pixels. So it will be something like 500 or 600 pixels. And if you know the pixel size, for example, like the pixel size we talked about, like 3 micrometer. The 3 micrometer times this number will be the exact focal length you have on your camera. Yeah, this is also the image sensor shifts. It's also in pixels. The camera extrinsics is a homogeneous transformation between camera frame and the world frame, right? It's just a rotation and a translation. Yeah, so usually you separate them, but essentially it's just transformation between two 3D systems, right? And if we write it together, it will look like this. There's a diagram over here. Some world point in the world coordinate system P, we can relate to the camera frame with the extrinsics, and the camera frame can be related to the image frame by the intrinsics. Yes, how do we get them? Yeah, how do we calculate them? For intrinsics, we can use the camera calibration, and this will be in the lab. So we can use this OpenCV functions to find these corners in the checkerboard. Then we just call the calibrate camera to do the camera calibration. It will output the camera matrix. It will also output a distortion matrix, like to help you correct the distortion in your image. So we can see over here, this is a distorted image. So distortion is usually because the design of the lens. Sometimes it's floored, or maybe not floored, but specialized in sharpness. So they have a lot of this distortion. And once you correct it, will be great. It will be great. But this would be an extra step if your lens is distorted. However, as we talked about the ISP, right, image signal processor, they can do it. They can do this transformation very fast. So your CPU don't have to worry about this if your lens needs a distortion correction. So yeah, camera calibration, use OpenCV, we can get this camera matrix. What about extrinsics? So to get this extrinsics, we are basically just computing a transformation, right? So there are ways to do this. We can just find enough corresponding points in the camera frame and the world frame, and with enough corresponding points, we can just solve the linear equation, right? One way or another, we solve for the homography, then there are methods that you can use singular value decomposition to separate the rotation and the translation. However, we don't raise in the world frame. We don't have the privilege to raise in the world frame. We would never know like exactly what is our location, what is our opponent location in the world frame. We have to do localizations on that. So our camera is aligned with the car's frame. So we can just directly work with the camera frame. In our case, in our F1TENTH course, you can see the camera frame over here. So next thing we'll talk about is distance estimation. That's when we have a point in the image, can we get the distance between the camera and that point in the real world? This equation over here, if we want to find the relation, we should just do the camera calibration, right? We can get the intrinsics matrix. And if our camera is mounted on the car without any angle, without any roll pitch at all, that's to say that this car frame, the axes are just overlapping with the camera frame, then we can have this relation. Of course, we would have a mounting height of the camera. So the camera is not mounted like on the floor, right? It has to have some mounting height. So this term we can put it there. Be sure to use the correct orientations. As you can see over here, the optical axis is actually Z axis in the camera frame, but to the car, the front is X axis. So we will have this relationship. And if we can look at the third row over here, this is the relation, right? If we can have the Z in the camera frame, that is exactly the same as the lambda. So if we put this together, rewrite everything, we'll have this relationship. And then if the object is on the ground, that's to say Z car is 0, right? Then we only need one pair of the corresponding points to find H, because everything we know, everything else we can get from either, for example, focal lengths, we can get from camera calibration, this and this from calibration. This is from the corresponding point. There's only one unknown over here. That's the mounting height. And once we have the mounting height, we can rearrange this thing so that if we can have a coordinate in the camera frame, I'm sorry, if we have a coordinate on the image plane with the image pixels, then we can calculate what is the coordinate in the camera frame. And since the camera frame has this relationship with the car frame, then we directly can transfer it to the car frame. So this will be in the lab. You just do a solving for this height, then we can use this height to calculate things that's on the floor. Of course, we're assuming everything is on the floor. Basically, we're trying to get, like, for example, if there is an obstacle or if there's an opponent car, we can assume that's always touching the ground. What if there are rotations in the camera mounting? Like camera mounting, we cannot guarantee it's always straight ahead, right? It could be some tilt, right? It could be that it's pan a little bit. So for this situation, for example, there is a tilt, then it's an extra unknown, right? Then we just need extra points. We can always solve the equations with extra corresponding pairs of points in the two frames. Yeah, we can just add more corresponding points to solve for any missing variable. The next topic, I'll talk about how do we do detection with OpenCV. It's useful for doing the vision lab. Yes, a lot of the detection nowadays are done with deep learning, of course. But it is good to know that you can have a very strict and logical way of doing this. So here I'm just showing you two very important functions that's very convenient to use as well in OpenCV. First is canny edge detector. A lot of you probably know this. It's just any high contrast edge with the right parameters, you can get them, and you can work on the edges if you want to detect something or measure something. The second is called the Blob detector, and there are different like customizations of what kind of blob you want to detect, like the area of the blob, how circle it is, what is the inertia like, or how connected the blob is. And when you define it, if you have a clear mind, the shape of the object you're trying to detect, you can use this function to detect your things very quickly. The second thing I want to talk about is the HSV color space. So what is a color space? It's how we represent colors. For example, we know RGB, right? We are using 3 basic colors and their combinations to represent the whole world of colors we see. It's represented by 3 values. HSV is just another representation of colors. It's called hue, saturation, and value. If we look at this diagram over here, hue is just like what kind of colors, right? Saturation is like saturation, how saturated it is. And this value is also called brightness or intensity. Like if the value is 0, it's 0. If value is really high, it means it's very as bright as it is possible. So HSV is sometimes more useful than RGB. That's because when in RGB, you probably for a human, like 2 color points may be very close, but in the RGB world space, the numbers may be very far apart. Like if we talk about like Euclidean distance, so it's hard to group colors in the RGB world, and we can use this function to convert color space. And here are the different value of the hue value. Let me give you an example here. Suppose you're an engineer in an autonomous lawnmower startup. An investor is coming tomorrow to see the prototype, so there's no time to train a neural network. Your task is to detect this lawn, the boundary of the lawn, with classical methods. Because we know, like, if we want to train a neural network, we need to detect, we need to collect data, we need to label data, then we have to train it. But there's no time. How do we do it? We can try the HSV methods. So I'm just going to show you very quickly how to solve it, and you will see it's very easy. First, we Gaussian blur it. The second one, we convert it to HSV, and we threshold the hue, because green and yellow, if you go back, green and yellow are very close. So if we threshold between, for example, here and here, we can get this natural color, right? So that's the next step. We can also saturate. We can also threshold the saturation, because usually any man-made things, the color saturation is very low. Any natural things, like biological things, usually the color saturation are high. So we can also use this to do this better. However, there are 2 blobs. Then we do a connected components. We detect there are 2 connected components, or there may be more. Then we can just filter out the smaller ones. Then the next step, we can use dilute or erode to filter out these small blobs, small cavities inside the blob. So just 4 steps, we can have a quite good detection on the lone boundaries. Right. Okay. Third topic in OpenCV. I want to talk about feature extraction. This is also like a foundation for the next lecture, the deep learning. So if we want to detect an object in an image, we always need to find features. So what is a feature? So you can see the picture over here. There are 6 cropped small images. The AB, you can see this is flat in the blue channel. This is basically flat, like it's not blue, but it's like it's kind of yellow, so it's a mixture of green and red. CD, we can see there's a clear edge over here. EF, we can see there are 2 edges that form a corner over here. So these are called features. It's either like spec, so we need to make special filters to respond to them. For example, if we have a filter that's responding to an edge in this direction, then the output of the filter will be very high for this feature. And if the object you're trying to detect, for example, if it's a car, we know that it will have certain circle that's wheels, so we can detect that. For maybe we can detect the edge that's on the two sides of the window, the windshield. That's also another feature. So the classical way of doing object detection is that we just look at the object, we see what features it has, and we design a filter that respond to them. What do I mean by filters? So these are called filters. It's a filter in the way that you can do 2D convolution on that. Let me put this over here. If you're not familiar with 2D convolution, is that you have this filter, you put it on another image. We can wait until it restarts. So this is called a sharpening filter. This is called a kernel. And for each position, for each pixel, or maybe there are strikes, for each position you want to do, you put this kernel here and you do this accumulation step, and you will get a result. That result will be showing over here. So F is the original picture. G's are the filters. For example, if it's only a one over here, that's unchanged. If it's like this one, it's probably a Gaussian blur, like Gaussian shape. It's a blurry image. For example, here we can see it's dimming one side and it's brightening on the other side. It shows vertical edges. So the weights G is often called a kernel or a filter. Kernels are with different weights will respond differently to features. Right. So this one is a vertical edges. We can have another one that's just for horizontal edges or something, and we can have a combination of them to detect a certain features. There are also like automatic feature extraction algorithms inside OpenCV. The first one is the Shi Tomashi corner detector. It's a corner detector, and it also outputs a vector of describers, like how if we have another image of the same object, can we detect like this is the same location? So all of this feature extraction method, they can output a vector that you can compare to another feature to see if you're looking at the same thing. The second one is called SIFT. It's scale invariant. That means if the thing is closer to you or if the thing is enlarged, it will still output the same descriptor vector, so that you can know that this is the same point as the other. However, this one is quite slow. The third one is called RAW, ORB, oriented fast and rotated brief. The fast and brief are two like different other methods, but I included here this because this one is quite commonly used in the world of classic computer vision. So it's because it's scale invariant. It's also orientation invariant. Like even if the object is rotated, it's still able to detect it. It's also very fast compared to the SIFT. So it has a quite long output descriptor vector. That means when you have 2 points to match, you actually are very confirmed if you have a large overlap between the 2 descriptor vector. So with this, we can basically match these features between frames. And if we can match features between frames, we can track objects, right? Yeah, putting it together, we can see over here if we can detect these points with the previously mentioned OpenCV methods, and just calculate the distance on the output descriptor method, descriptor vectors. If they are very close in those vectors, we know that's the same. It's the same point, right? So if we have all these corresponding points, we can basically tell how the camera has moved, right? And if we do it with the continuous video, we'll be able to track the motion along a path. So yeah, we can find unique features in image and match between frames. Then we can find their coordinates in the world frame with the camera model. Can we use them as landmarks in SLAM? Because we can find them in the world model, right? So they are all landmarks. That's why I'm going to enter the topic of Visual SLAM. Okay, Visual SLAM framework. First step, we have to get feature extraction and feature matching. We extract and match visual features between camera frames. Next step, visual allometry. We calculate the motion between the consecutive camera frames. Third, it's called bundle adjustment. Is to correct the transformation with historical data. This is a key component in Visual SLAM, and we'll talk about it in the next slides. So for now, it's basically just we use all the previously recorded data. Can we optimize the movements altogether, not just between frames, but with the whole history of the points, the features we captured along the track. It will also be doing map building because it's a SLAM. We don't have the map. So for example, you can see over here that it is always doing feature detection and accumulating them to build a map. Another important part is the loop closure, is that when we encounter the same location the second time or even third time, can this algorithm detect that we return to the same point? And because usually you're able to do local detections very well, but your paths may just drift over time. So when you come back, your odometry basically probably shows that you are not in the same position. So can your vision part correct it by doing this loop closure? Okay. First, we'll talk about is called the bundle adjustment. So the bundle adjustment is optimizing the camera projections by considering all points in cameras. It's all points in cameras, so they are all points, right? It's just the history of all the features we get. What are all cameras? It's treating cameras from different time as different camera. So it's not that we are considering them old frames. We're basically considering everything happen at the same time. And we just have multiple cameras at multiple positions. However, we don't know whether those positions are correct, but we know that we're looking probably at some overlapping between frames. So with this kind of knowledge, can we optimize this altogether? It usually starts with the initial guess, like it's treating cameras from different times as different cameras. It is a non-linear optimization because cameras usually have rotations and distortion corrections, etc. But statistically optimal, but it's also very expensive to do because you're calculating with so many points. So, mathematically, what we look like this. It's not very complicated. It's just trying to help you understand what's really doing over there. So here we have a relation between the image pixels and the world frame, right? We don't know this, but this relation should look like this. So if we write it like with this vector form. P is the whole this part, it's the projection part. This is the pixel coordinates. This big X is the world coordinate system. And this lambda is just a lambda, a scale factor. So I is for each point, we can write like this. This is a relation between each point we find in an image and each point in the world frame. Next is we consider many points and many cameras. Remember, old cameras are not old cameras, it's just different position cameras. And we probably have some overlap between the two frames. So camera J would have a different sets of points, different projection because it's at a different location, and it may just have a different scale factor and different pixels, but they probably would overlap at some pixel locations, right? So this is with the perfect ones. If it's not perfect, if the projection is not perfect, if it's arbitrary projection, then this would have an error term, right? Between this arbitrary projection from the world frame and the actual pixels, there will be some error term. And that's it. The other things, you just give it to the whatever nonlinear optimization algorithm you can find. So for each pixels, for each cameras, you just optimize so that you get a projection that produce a minimum error term. This one over here is just that sometimes it's 0 when point I is not seen by camera J. So that when they're not overlapping, you don't count them into the whole error term. So boundary adjustment, that is that you have all a bunch of cameras and points. You do this very expensive optimization, you can get better projections between your locations, your different frames. So we do this because just between two frames, sometimes they're really noisy, and we can get error terms, and we can drift very easily. But if you can optimize the whole history altogether, this usually will produce a better result. So some challenges in Visual SLAM. As you can see over there, we have exponentially increasing number of feature points to match. Like we have to find it for each point. We have to match for each other point, right? We need to find if they are overlapping between a old frame, or are we at the end of the loop? Like, are we walking back to the same location? And this boundary adjustment is especially expensive. Can we work on monocular camera without IMU? Like we don't have a correction of the drift, or we don't have a correction of the sudden movements. Sudden movements are usually you just lost everything with visually, right? Your features may not overlap at all. So we probably want a very fast, like global shutter camera for doing that. And yeah, can your algorithm handle drifts? Can your algorithm close the loop? So I'll be talking about this ORB SLAM. Next slide. Here's just some plots that this does. It's a comparison between two SLAM algorithms. ORB SLAM. So this is an algorithm that's quite popular. Another popular one is the Open Visual SLAM, but that one, they closed the GitHub repo, but we still have this open source. So the way this algorithm attacks the three challenges is that the first thing is it separates out tracking, map building, and loop closure. So it used a different algorithm for loop closure and then the tracking. We know tracking is, it's got ORB slam. That's because they use this ORB feature extractor. So for tracking, it's just you have 2 frames. Then you do feature extraction. And you find the feature matching, right? And you save it into the whole map you have. And you find another frame and you do the feature matching again. But however, if we do this map will just grow very fast, right? So ORB slam, they have a selection of keyframes and curling policies for keyframes and points. That's between some time or between some distance, they will select one frame as the keyframe. And the keyframe is stored on the essential graph. The whole idea is if we look at the map globally, we don't see the points between the keyframes. We only see the keyframes. That's the third point. It's separating the separation of global and local information with this co-visibility graph and the essential graph. So for co-visibility graph, it's used as a local a feature matching problem. It's only matched to some time or step distance. So, however, on the essential map, it's only showing the keyframes. So what's the use of the essential map? So it's the third part, the loop closing. So they use a bag of words for place recognition. So bag of words, it's another descriptor vector that's different from the ORB. It's using the distance between the points, the relative shape of the points, as like words, and we'll have a collection of those features to recognize if this place is a previous place that I've already visited. So this is the loop closure process. So in general, SLAM algorithms are quite useful in like static environments where there's no dynamic obstacles which changes positions as we go along the path. We probably need extra threads to deal with dynamic changing obstacles because they'll mess around with the feature matching. So I think this can be a quite interesting final project proposal if some team are interested in using the F110 car to do the visual slam. Okay, that's the end of this lecture. Thank you for your time, and I see you in the next one.